A twin prime is a prime number that is greater than or less than another prime number by 2. We often refer to twin primes in pairs. For example, the smallest pair of twin primes is 3 and 5. Other examples include 5 and 7, 11 and 13, 17 and 19, and 29 and 31. The Twin Prime Conjecture states that there are infinitely many pairs of twin primes, but at the making of this video, it has yet to be proven. A cousin prime, on the other hand, is a prime number that differs from another prime number by 4. Pairs of these include 3 and 7, 7 and 11, 13 and 17, 19 and 23, and 37 and 41. Some cousin primes are also twin primes, such as 3, which is twin with 5 and cousin with 7, or 71, which is twin with 73 and cousin with 67. If a prime number is 6 more or 6 less than another prime number, it is called a sexy prime, a name that, of course, stems from the Latin word sex, meaning 6. Examples of sexy prime pairs include 5 and 11, 13 and 19, 17 and 23, 23 and 29, and 31 and 37. Some sexy primes, such as 11, are also twin primes, and some, such as 13, are also cousin primes. In our discussion up to this point, 13 has appeared as a twin prime, a cousin prime, and a sexy prime. We could say 13 is a sexy twin cousin prime. 41 is another example of such a number, being twin with 43, cousin with 37, and sexy with 47. Other examples of sexy twin cousins include 7, 11, 17, and 19. Notice that for each of the sexy twin cousin primes we just mentioned, the numbers twin, cousin, and sexy counterparts do not all lie on the same side of the number. There's always at least one above and one below. We might wonder if this must always be the case, or is it possible to have a prime number for which the twin, cousin, and sexy partners are all less than or all greater than the number itself? In other words, does there exist a prime number p such that p plus 2, p plus 4, and p plus 6 are also prime? It turns out that such a prime number does not exist, and we can prove it. Since the only even prime number is 2, all twin, cousin, and sexy primes are odd. Therefore, finding a prime number p such that p plus 2, p plus 4, and p plus 6 are also prime boils down to finding 4 consecutive odd numbers that are all prime. We certainly do not get this result if we start at the first odd prime, 3. Although 5 and 7 are prime, 9 is not since it's divisible by 3. We can also rule out starting at 5 and 7 since those sets of 4 will also include the composite number 9. Although we probably wouldn't consider starting our list at 9 since it's not a prime number, doing so gives us a hint as to why we'll never be able to find 4 consecutive odd numbers that are all prime. Notice that if we start at 9, the final number in the set of 4 is 15, another number that is divisible by 3 and therefore not prime. Move up 3 more odd numbers from there and we arrive at 21, yet another number divisible by 3. Continuing in this fashion reveals that every time we go up another 3 odd numbers, we arrive at another number that is divisible by 3. The reason this result occurs is that every time we move up 3 odd numbers, we're adding 6, and adding 6 to a number divisible by 3 gives another number that is divisible by 3, since 6 itself is divisible by 3. Therefore, no matter where we start a sequence of 4 consecutive odd numbers, we're guaranteed that the set will include at least one composite number that has a factor of 3. Finding 4 consecutive odd numbers that are all prime is impossible, and thus a sexy twin cousin prime with the twin, the cousin, and the sexy all above or below cannot exist.